let's try to solve this system of differential equations. Well, the first thing that I like to do is I'd like to know if I can solve this. I know how to solve first order linear systems of differential equation. So let's see if each of these equations are linear. So to see if it's linear, I'm going to look at the dependent variable, in this case x, and I'm going to check that x and all of its derivatives are to the power of 1. Well, in this case, I can see that this is to the power of 1, and this is also to the power of 1. That's great. So that criteria is met. Now the second criterion is that the coefficients of the derivatives or of the dependent variable have to be all at most with respect to t, or the independent variable. In this case, it's not even with respect to t. It's just a constant. And so that gives me confidence that this is a linear first order system of differential equation. But I have to check this one too. Here we have the y is the dependent variable, and this derivative is to the power of 1. This is also to the power of 1. Everything else is with respect to multiplied by t in all of the coefficients here. So I can say that this is linear as well. Now, is there a way to rewrite this in matrix form? Because that's how I have been taught to deal with these types of systems. So, yes, we can rewrite this. We'll say this is x prime, and this is y prime, and we'll imply that the independent variable is t. Here, since these are already aligned, I can easily pick the coefficient matrix, which is called like that because it's the coefficients, it's composed by the coefficients of all of these terms. And then we have x and y. And this might be the hardest step, realizing that this x goes with this column. And so you see right here why we lined it up for that same reason. But once you get the hang of it, that should become second nature. So now that we have this, what do we do? Well, let's realize that this is this form right here. And I'll call this k, just to make it different from the letters inside. So this is going to be k prime. I can say that this is my matrix A, and I can say that this is just my k. So I notice that this is a homogeneous system. So what can I do with that? Well, let's say I guess that the solution is e to the lambda t, but in vector form. So I'll say that my solution is this. Now, why did I guess that? Well, because this has a similar form to just the scalar, the scalar form like this, where we had the x prime, number, any number, let's say b, and then x. And this really reminds me of this, where if I take the derivative, I'm just going to get, and if I have an a here, I'm just going to get this. And this is what we're getting over here. We're getting that the derivative is just the scalar factor of that original solution. So that's why this is a relevant guess, I would say. Well, if that's our guess, then now let me call this x. So this is x prime, this is x. So if that's our guess, then our x prime is going to be, I'm assuming that k is just a constant, a vector that is constant. So each entry does not have a t in it. And I take the derivative of the part of the solution that changes with time, which is e to the lambda t. And the derivative of e to the lambda t is going to be lambda. Then we have our k that just stayed in front, e to the lambda t. Well, now I can substitute this back into here. And let's see what we get. So x prime, that's going to be lambda k e to the lambda t is equal to the matrix A times k e to the lambda t. Okay, well, the first thing I notice is assuming we're not in an interval for which e to the lambda t is going to be equal to 0, which is not actually possible, because even when you have t equal to 0, e to the 0 is still 1. So we can divide both sides by e to the lambda t. So, oh, sorry. This would be a 1, and this would be a 1. And then we have the following expression. Sorry, the following equation. Now, I notice that this is scalar multiplication, and this is matrix multiplication. So the first thing that I want to do is I want to make this matrix multiplication by including the identity matrix, which is kind of like expliciting the 1 in a scalar equation. Now I'm going to flip the equation, so I'll bring ak to this side, and we'll continue over here for spacing purposes. So I'll bring ak, so I just flipped the equation here, lambda k, and now I'm going to subtract lambda ik to both sides. So we're going to get ak minus lambda, which is just a scalar, remember. I is the identity matrix, and k is a vector. And that's going to be equal to the 0 vector, because we're dealing with vectors and matrices here. Now what I can do is I can factor out the k, and I have the following expression. A minus lambda I times the vector k is equal to the 0 vector. So how can this happen? Well, there's two ways that can happen. So either k is equal to the 0 vector, and then whatever transformation you apply to it, it's going to stay the 0 vector. But another way is if this determinant, so if this transformation, because remember this is the matrix A minus lambda times I, which is another matrix, so it's an overall matrix. And if that matrix collapses the vector to a lower dimension, which means that its determinant would be 0, then this equation would also be true. So this is called the trivial solution. Trivial solution. And this is the eigenvalue problem. Now, why is this the eigenvalue problem? Well, because, look, this is the statement that we got at a certain point. And that is there a transformation that applied to a vector gives me that same vector multiplied by a scalar? Remember, that I does not have to be there. So we could actually go all the way back to this right here. This is the eigenvalue problem. This is the eigenvalue problem. I want a value of lambda that is the result of applying the transformation matrix A to K, meaning two things. First, this value lambda is related to that matrix A, but only related when you apply it to a specific type of vector, which is the vector that only gets scaled but not knocked off of its span. And I did talk about span earlier in some other playlist. You can go and refresh your memory with that. So this is what we're doing to solve our homogeneous system. So let's solve that. So how do I indicate the determinant of a minus lambda I? Well, to indicate determinant, I'll do that later. So we have a. What is a? Well, we said a is -4, -5 halves, and 2 and 2. Okay. Well, now I'm going to rewrite that expression. So we have minus lambda times I. I has to be the same size as this one to make it something that we can do. So, and it's the identity matrix, and it's going to have 1 in the diagonals and zeros everywhere else. And we want to find the determinant of this. So let me put this in parentheses here, like this. And let me say that the determinant of that, and we want that determinant to be equal to 0. So the first thing that we do is multiply lambda by the identity matrix. So we're going to rewrite a -4 and 2, -5 halves, and 2 here. And then here, minus lambda, 0, 0, lambda. We close this part, and we set it equal to 0. Now we can execute this, this subtraction entry by entry, because these are both 2 by 2s. We engineered it that way. We put the I that had the same, the identity matrix that had the same dimensions as the A matrix. So now I can actually write determinant this way by using the vertical walls, and we got -4 minus lambda, 2 minus 0, which is just 2, -5 halves minus 0, which is just -5 halves, and 2 minus lambda, 2 minus lambda. Now we close this, and we set it equal to 0. Now to find the determinant of this 2 by 2, we multiply this entry by this entry and subtract this entry by this entry. So let's do that, and I will factor out a negative sign along the way. So if I factor out a negative sign from this term, I get lambda plus 4. And then I want to multiply it by, well, I'm going to factor out a negative sign again, and there I get positive lambda minus 2 because I factored out a negative sign. And then I'm going to subtract 2 multiplied by -5 halves. And that has to be equal to 0. So the first thing I notice is that this negative and this negative cancels out. Then I can expand this, and knowing the pattern, I know that this is going to be lambda squared, then the sum of these multiplied by lambda. So what is the sum of 4 minus 2? That's going to be 2 multiplied by lambda. And then we have the multiplication of these two, which is going to be -8. Okay. And then these negatives cancel out, so we'll get a positive. The 2 and the 2 cancel as well. And so we only have a 5 here. And all of that has to be equal to 0. Okay, well, since this is getting kind of long because I wanted to show you where the theory came from, we'll do a part B. And I'll see you next time. And I encourage you to actually finish this on your own and then check it. All right, happy studying.